In this video, we are going to talk about the method of undetermined coefficients and specifically the superposition principle, and using that to help us find the particular solution that we need when we have a non-homogeneous linear differential equation. And this method only works when you have functions on the right-hand side, when you have something that's in the form of, let's just say, for example, plus y prime plus 2y, and I'm going to have equals 6 on the right-hand side. That right-hand side needs to be a constant or linear or quadratic or cubic or some other kind of polynomial like that, or it needs to be exponential, or it needs to be some combination of sine and cosine, but not tangents or secants or cosecants or cotangents. Let's see what else. It can be the product of those types of functions as well, sums and differences of those, but we need to be able to look at that and be able to see that it's one of those, that it's a linear combination would be the term of those elementary functions. So polynomials, exponentials, and sine and cosine are the main things that we're looking at. And it can be the product of those things too, not just linear combinations, but it can be products of those things. So let's go ahead and let's start with our auxiliary equation that we talked about last time, as if this were homogeneous, what our part would be that would come from the from this being equal to 0. And we're going to call that the complementary solution. YC is equal to E C1 e to the negative x plus C2 e to the negative 2x. My total solution y is going to be equal to yc plus yp. I'm going to look at a choice for yp here, something that I want to add to yc that's going to get me a constant. I know when I do all this and I have just these parts, they're going to give me 0. So I need something that I'm going to be able to add in here to get just the 6. So I think it's just going to be a constant, because when I take the derivatives of a constant, it's 0. I'm going to have a constant part left over here. So I think it's just a constant, and that's what my superposition principle tells me to try. So I'm going to try yp is equal to a constant that I'm going to call capital A, just using constants just like I would in partial fraction decomposition. The only capital letter that I probably want to avoid using is a capital D, for reasons that you'll see in our next section when we come back and we talk about the annihilation approach. And capital D is used as an operator in differential equations to say that you're taking the derivative of something. So it's an operator, so you probably don't want to use capital D as a variable. So other than that, you should be okay to use every other letter of the alphabet, and we usually use capital letters for those. So I'm going to just go ahead and stick in the equation here, yp double prime, that's going to be 0 plus 3 times yp prime is 0 plus 2 times yp, that's 2a, needs to be equal to 6. So we have 2a is equal to 6. A is equal to 3. So my y should be my yc plus my yp is just 3. All right, let's look at another example. I'm only going to do a few examples in this video that are pretty basic, and then I'll come back and do another video with some more that are a little bit more complicated. So let's just get our feet under us with this video here. First things first, let's look at what happens with just this homogeneous piece, and we'll set up the auxiliary equation for that. And that has a repeated root. So my complementary solution, C1 e to the 5x plus C2x e to the 5x. I don't see anything on the right-hand side with an e to the 5x in it. So there's nothing in my particular solution that is already in my complementary solution. We'll see what happens later with that. So I think my yp is just a linear equation that I'm going to call ax plus b. And that means yp prime is going to be a, and yp double prime is going to be 0. Come back and make this 0 minus 10a plus 25 times ax plus b needs to be equal to 30x plus 3. So this is negative 10a plus 25ax plus 25b equals 30x plus 3. Using a system of equations here, 25a for my x parts needs to equal 30, and a is equal to 30 over 25 is 6/5. Then I have negative 10a plus 25b needs to be equal to 3. We just solved for a being 6/5 plus 25b is 3. 5 goes into 10 2 times, so that's negative 12 plus 25b is equal to 3. 25b is going to be equal to 15, and b is going to be equal to 3 over 5. So we have my total solution y is equal to my yc plus my yp Let's look at another example here. And let's set up our auxiliary equation for the homogeneous equation. 1/4 m squared plus m plus 1 equals 0. I don't really like that fractional coefficient, so I'm going to multiply everything by 4. It has the same solutions here. So that's going to make this m plus 2 squared equals 0. M equals negative 2, multiplicity 2. And so my yc is going to be equal to C1 e to the negative 2x plus C2x e to the negative 2x. And I don't see e to the negative 2x anywhere over on the right-hand side, or x e to the negative 2x. So I'm going to have my yp is going to be something quadratic, ax squared plus bx. I really don't need the plus c part, but I'm just going to put it there just as a generic quadratic. But I think I might. So I might need the constant just because of the derivative here throws a constant and the derivative here throws a constant. So I might need a constant to balance it out. I might not, but we'll see. So yp prime is equal to 2ax plus b, and yp double prime is equal to 2a. So we have 1/4 of 2a plus 2ax plus b plus ax squared plus bx plus c needs to equal to 1x squared minus 2x plus 0. So this is going to be 1/2 a plus 2ax plus b plus ax squared plus bx plus c equals 1x squared minus 2x plus 0. Let's get everything in descending order on the left-hand side. Ax squared plus 2a plus bx plus 1/2 a plus b plus c is equal to 1x squared minus 2x plus 0. So a is equal to 1. 2a plus b is equal to -2. A is 1, so 2 times 1 plus b equals -2. 2 plus b is -2, and b is a -4. And then 1/2 a plus b plus c equals 0. So 1/2 of 1 plus a -4 plus c equals 0. It's going to be 1/2 minus 8/2 plus c equals 0. -7/2 plus c equals 0, and c equals 7/2. So y is equal to yc was, back up here, c1 e to the -2x plus c2x e to the -2x plus my yp is going to be 1x squared. And then b was -4, so minus 4x, and then plus 7/2. All right, I'm gonna stop this video here. Those again were just some really basic examples. I'll come back next time and deal with some other examples that have exponential and trig functions in them. Exponential aren't really that difficult either. I just didn't get to any of those this time, but since we're almost at 15 minutes, I'll go ahead and stop here, and then I'll come back and talk about some very similar problems to these, and we'll use a different method, not the superposition principle, but we'll use the annihilator approach, and we'll talk about what the annihilator is and what annihilates what. So look forward to that coming up. Again, the annihilator approach also works for the same types of functions here. It's really not going to help you with any other types of functions. You're still going to have polynomials, exponentials, sine and cosine functions, products of those, sum and difference of products of those that's basically going to be it. It's not going to help you with logarithmic, with anything that really changes form when you take the derivative. So polynomials stay polynomials of a lower degree when you take the derivative. Exponentials stay exponentials when you take the derivative. Sine and cosine go back and forth when you take the derivative. So you'll see that you have to include both pieces for them, but we don't want to include anything like logs that become rational functions when we take the derivative, or rational functions that when you take the derivative, the exponent, it becomes more complex when you take the derivative, or inverse trig functions, or I guess technically hyperbolic sine and cosine could also work in this because they flip-flop back and forth, but we wouldn't want anything like the derivative of tangent to secant squared where the function changes. All right, so you get that idea, that things where you can easily predict what is going on with the derivatives, and it pretty much doesn't change the type of functions that you have. That's where you're going to be using the superposition principle with undetermined coefficients, or the annihilator method that we'll come back and talk about in a little bit. All right, that's it for this video. We'll see you next time.